This video is not about contents of the lecture series, but it's more about, as the title already suggests, preliminaries. It's about notation and other things that you probably already know, but which are going to be dealt with later on during the lecture series. So it's important that you immediately understand it before you are going to the lecture series. Well, as I already said, this is mainly about notation and definitions. So let me immediately start with these definitions. And before I'm going to say anything, you know already for a long period of time that the econometrics that we are going to discuss is related to statistics. And of course, statistics is related to probability theory. So most of the times I'm going to talk about probability theory. So therefore, many times I will introduce so-called random variables. And this is going to be the most important, I'm going to use capitals for these random variables. So at the moment that you see a y, x, a u, or a v, you immediately should realize that these must be random variables. Another thing that you already know of is, of course, that random variables, they cannot have predetermined outcomes. So that it implies that we cannot just say like y, for example, is equal to 1, 2, 3, or 5. But what we can say is that they have probabilities. They have probabilities that they're going to have some kind of realizations, and we're going to denote these realizations by small letters. So at the moment that we're going to see a small y, then most likely it's going to be related to this large y that we've over here. So it's going to be the realization of this large y that we've over here. But as I already said, random variables have probabilities. And one of the most important probability is related to the so-called distribution function. The distribution function is nothing else as the probability that y is smaller or equal to this realization little y that we have over here. And the notation that we're going to use is that we're going to use a capital F. So capital F's are not going to be, say, random variables, but they're going to be, well, just the distribution functions. And we're going to use this subscript y that we have over here in order to indicate that it's going to be the distribution function of this random variable y that we have over here. And it's going to be evaluated in this little y that we have over here. Important to realize is that it's not only the case that random variables have always a distribution function, but we can even say that a random variable is, say, completely determined by its distribution function. So at the moment that you know the distribution function of a random variable, then you cannot know anything more from that particular random variable. Well, we know already that random variables can be either continuously or discretely distributed. At the moment that we are going to look at the continuous distribution, then in most cases, we're also going to look at the so-called density. The density that we denote here by a little f is nothing else as the first order derivative of the distribution function. We will sometimes use this notation, dfy, that we have over here. I'm pretty sure that you have already seen this before. Well, this dfy actually is going to be a probability at the moment that we're going to have a discretely distributed random variable. And it's going to be the density at the moment that we're going to have a continuously distributed random variable. Then in addition to that, I'm going to introduce some definitions. First of all, I'm going to look at the support. The support of a random variable y equals the minimum set for which fy is strictly increasing. So that means that it's actually nothing else as the unions of interval and support points for which we have that the distribution function that we have over there is going to be strictly increasing. At the moment that we have a discretely distributed random variable, well, then the support is actually nothing else as the union of all the support points. So for example, at the moment that somebody is going to throw a dice, well, with the dice, we can only throw 1, 2, 3, 4, 5, or 6. So that means that that's also going to be our support. At the moment that we're going to look for a normal distribution, well, then you should realize that the normal distribution is actually increasing over the whole real line. So that means that the real line in this case is going to be the support. Well, I will denote supports by calligraphic letters. So that means, for example, that at the moment we're going to look at this random variable x that we have over here, then the calligraphic letter x is going to be the support of this, say, random variable x that we have over there. Another definition that I'm going to introduce is here equality in distribution. A random variable x is said to be equal in distribution to another random variable y whenever the distribution functions are equal on every support point. The notation I'm going to use here is that at the moment that x and y are going to be equal in distribution, then I'm going to use here x equal to y, but above the equality sign, I'm going to use a d. That is in order to denote here that we have here equality in distribution, and take into account that that's not the same as at the moment that I would have written down x equal to y without this d that we've over there. Because if I write down x equal to y, then x and y are not only equal in distribution, but they're even equal in outcome. And there is a difference between the two. In order to explain that, the best thing to do is to look at a very simple example. Suppose I'm not going to throw one dice, but suppose that I'm going to throw two of them. First the first dice, and second the second dice. And well, what I can do is that I can use the outcomes of the dice for random variables, of course. And x is going to be for the first dice, and y is going to be for the second dice. We should realize that, of course, at least at the moment that both dices are going to be there, then that at that moment in time, x and y, they're going to be equal in distribution. However, they're not equal in outcome, because equal in outcome means I'm going to have exactly the same outcome for the first and the second one, and that's of course not true. The next definition I'm going to use here is the definition of IID. For that, I have to introduce a so-called sequence of random variables yi. So here what we're going to have is that we're not going to have just one particular random variable y, but we're going to have a bunch of them. We're going to denote them by yi, and I runs here from 1 to n. Any is here also important because of the fact that n in my notation will always be the sample size. And now that means, of course, that we are going to introduce here not just one random variable, but we are going to introduce n of them. And we're going to say that this sequence of random variables is said to be IID, independent and identically distributed, whenever, well, first of all, well, the name already suggested, they have to be equal in distribution. So therefore, y1 is equal in distribution to y2 up to yn, of course. But in addition to that, we also have independence, and that means nothing else, as you already know, of course, that is that the multivariate distribution of y1 to yn is going to be nothing else as the product of the marginals. Well, another, say, notation that I'm going to use over here is that usually the y that we have over here is going to be the outcome variable. X is going to be a regressor, that can of course be a vector, and u and v are simply going to be error terms. I would like to go on with the next topic, and that's the topic of estimation. Central in econometrics, that you know already for a long time, is that we would like to estimate parameters of models. Well, that's not completely true, by the way. You should realize that at the moment that we do not have parameters, that's typically the case at the moment that we're going to look at non-parametric econometrics. Well, then at that moment in time, we can of course not estimate parameters if we don't have them. And we typically are going to estimate objects. And in most cases, during this lecture series, it's not going to be so much that we are going to estimate parameters, but we're going to estimate these objects that we have over here. I'm going to denote objects, or say parameters. I'm going to denote them by a Greek letter. Typically, we call them estimates. Estimates are nothing else as things that we would like to estimate. So an estimate could be either a parameter or this object that we have over here. But then we also have two other things, and these are so-called estimators and estimates. And take into account that there is a big difference between the two. You should realize that estimators, first of all, they are what you could say, they're recipes in order to estimate something at the moment that we have a data set. So therefore, they're recipes that could be compared to a recipe at the moment that you, for example, would like to bake an apple pie. You want to bake an apple pie, then what you typically do is that you're going to say, look in a cookbook, or nowadays you would rather go for Google, and then in Google you're going to find out, well, a recipe. And if you're going to then follow all the steps that are in that particular recipe and you have the correct ingredients, then in the end what you're going to get is an apple pie. But you should realize that the recipe itself is of course not the apple pie. Well, the same actually holds true for the estimator. You should realize that an estimator is nothing else as a description what you could do at the moment that you have a data set in order to estimate the estimate that we have over here. So estimators by themselves actually do not have predetermined outcome. You should realize that they are random variables because of the fact that what we typically assume in econometrics is that the data comes to us in a random way. Data in that sense is not the thing that you actually have in your computer, for example, in an Excel file. But what we assume is that data is actually coming to us in a random way. It has some kind of data generating process. And therefore, because of the fact that data is, say, random, estimators are also random. Every time that we get another realization of the data set, that of course also implies that our estimator is going to be different by following, or our estimator is going to have a different outcome by following the steps that are in the recipe of the estimator. However, at the moment that we do have a data set, then we will have outcomes, we will have realizations of this estimator that we have over here. And these realizations we typically call estimates. So estimates are nothing else as the realizations of these estimators, these random variables that we have over here. I would like to go on with the next topic, and that's the topic of convergence in probability. Well, before I'm going to do that, I first of all have to make a first definition, and that is the definition of a random sequence Bn. A random sequence Bn is a random variable that depends on n. Well, that is quite simple definition. So it's actually nothing else as a random variable that depends actually on the sample size. Now, the main question always arises, what does it mean that a random variable depends on something, in this case, on the sample size? But that means, of course, not that the, say, random variable, the outcomes of this random variable depend on the sample size. But it means nothing else is that the distribution of this Bn that we have over here depends on the sample size. You can think of a particular example. Suppose, for example, that we're going to look at the so-called sample mean. And everybody knows that a sample mean is nothing else than the sum over all the observations that we have divided by the number of observations. This thing that we have over here. And of course, that depends on the sample size. You should realize that at least at the moment that the sample size is going to increase, we do know that the variance generally is going to decrease. And that, of course, means also that, say, the distribution of this Bn is going to change with respect to the sample size. Now I would like to go on with the second definition that we have over here. And that's the definition of convergence in probability. But what I'm going to do is that what I'm going to simply, well, read first the definition and then I'm going to try to explain it. The random sequence Bn is said to converge in probability to B whenever the limit of n going to infinity of this probability Bn minus B smaller than epsilon is going to be equal to 1. This is the definition of convergence in probability. What I have to say is that I always find this, say, definition one of the most difficult things to actually explain. And the reason behind that is because of the fact that there are many things in here. We have here Bn minus B smaller than some particular epsilon, which can be any number above 0, of course, and then we have this limit as well with n going to infinity. So that actually makes it really, really difficult to understand this thing that we have over here. But the best thing to usually do is to, first of all, ask yourself, what did it actually mean at the moment that in calculus, first year calculus, we're going to have, say, a particular sequence, say little bn, that converges to b. Well, we know already what that means because of the fact that that means nothing else as that the difference between b and minus b in absolute values, well, what we're going to have is that difference that actually is going to become, well, smaller and smaller and smaller at the moment that n goes to infinity. In a sense that it would always be possible to have any value of epsilon that we have over here, but larger, of course, than 0. And then it's always possible to choose an n for which we do know that the difference between b and minus b is going to be smaller than this epsilon that we have over here, whenever n is going to be larger than that particular, say, value that I give. To give you an example, suppose, for example, that we're going to have 1 over n. We do know that 1 over n is going to converge towards 0. B then, this small b that we have over here, is then going to be equal to 0. What does that mean? Well, at the moment that someone is going to say like, well, I make epsilon equal to 1 over 100, well then, of course, we know that if n, the n that we're going to choose, is larger than 100, well then the difference between 1 over n minus 0 is going to be smaller than this 0.01 that we had. If somebody says like, well, I would like to have it equal to 1 over 1000, then we just choose n to be equal to 1000. Can take any kind of value. Well, and then we can simply take the n that we want. Well, most important with respect to this, I'm pretty sure that you have heard about this before, is that you should realize that at the moment that we're going to look at random variables, this doesn't work. And the reason behind that is simply because of the fact that, well, random variables do not have predetermined outcomes. So we cannot talk about the difference between, say, bn and b, this large bn that we have over here, and b. We cannot talk about that difference. The reason behind that is because of the fact that we do not know what bn is. However, what we can do is that we can talk about the probability between bn and b. So we can look at the probability. This is not just talking about the difference, but this is going to talk about the probability of the difference that we have over here. And now, convergence and probability means nothing else is that what we're going to look at is what the probability that is that bn minus b is smaller than some epsilon. And if we are going to have, say, in this case, you should realize that even though bn itself is a stochastic variable, it's a random variable, it's a random sequence, you should realize that this probability by itself is, of course, not a random sequence. It's a, say, deterministic sequence. This actually does have a particular value, of course, for any epsilon that we have over here. And therefore, what we can do is that we can look at the difference between this probability and 1. And then what we would like to have is that this probability and 1, the difference between that and absolute values, is going to converge towards 0 in exactly the way as we typically have in a deterministic case. Well, the notation that we're going to use generally is that at the moment that the random sequence bn is going to converge in probability to b, then we're going to use this right arrow that we have over here. Bn converges to b, and we're going to place a p above it in order to, indicate that this is convergence in probability. Now, suppose that we're interested in a parameter theta, and we are able to arrive an estimator theta hat n. Question, of course, arises, how do we get this? Well, that's in this case not that important. Then we have the following definition. The estimator theta hat n is consistent whenever theta hat n converges in probability to this theta that we have over here. Now we should realize that consistency is always the most important, say, characteristic that an estimator can have. And the reason behind that is because of the fact that what does it actually mean that theta hat n is not going to converge in probability to this theta that we have over here? Well, that means, of course, that even in the case that we have, say, n going to infinity, so even in the case that we are in the, say, hypothetical situation in which n goes to infinity, which we typically don't have because we don't have that much information, in fact, about our, say, population that we are going to look at. But suppose that n goes to infinity, then even in that particular situation, we are not going to have that our estimator is going to converge to a correct value. Well, then it's of course going to, well, converge not at all, or maybe to another value. And we should realize that that's of course a very, very bad characteristic of an estimator. So therefore we should see consistency typically not as one of the, say, characteristics that a particular estimator can have, but you should take into account that this is the first thing that we should always check at the moment that we have an estimate, whether it's consistent or not. As soon as we see that an estimator is inconsistent, well, then we shouldn't use it. Estimators which are inconsistent are so bad estimators that it's actually better not to have an estimator at all. So therefore, this is always the first thing that you should check at the moment that you're going to look for an estimator. Well, related to the previous slide is the law of large numbers. A special case of convergence is the law of large numbers. In order to introduce this law of large numbers, suppose that we know that we have this sequence yi that is a sequence of IID random variables. We're going to assume, we do not know that much about this yi that over here, but at least we're going to assume that the mean of y1, and therefore the mean of any of these yi's that we have over here, is equal to mu, and mu is smaller than infinity. Then we are going to define the sample mean. Well, already have introduced the sample mean before, the sum of all the observations divided by n. I'm going to denote it here by y over line n. Well, then you can show that y over line n, the sample mean, is always going to converge in probability to the mean of y1 that we've over there. We typically say that the sample mean always converges to the so-called population mean that we've over there. That's a very nice, say, characteristic, and that's the law of large numbers. At the moment that we look at the law of large numbers, then we should realize that the law of large numbers is very important, but it even becomes more important due to some other theorems. And one of the most interesting is the continuous mapping theorem. What does it say? Well, it says that suppose that a particular random sequence Bn goes in probability to B, and there is a g function that is continuous around a constant b, then it is also the case that g evaluated in Bn, take into account that this is a random sequence because of the fact that, well, Bn is a random sequence, so g evaluated in Bn is a random variable. More in particular, it's a random sequence. That random sequence then is going to converge in probability to g evaluated in B. This thing is, of course, not a random variable. Let's look at a particular example. Suppose that we want to estimate not mu, but mu squared. So the, say, population mean, but then squared. Then what we can do is that we can consistently estimate this by the sample mean, but squared. The reason behind that is because of the fact that we should realize that we already know from the previous slide. Law of large numbers says that, well, the sample mean always is going to converge in probability to the corresponding population mean, and we should realize that the function gx is equal to x squared is continuous, of course, everywhere. So also in this mu that we have over here. So therefore what we can see is, well, G evaluated in Y overline, so in the sample mean, according to the continuous mapping theorem, is going to converge in probability to G evaluated in mu. Well, that is by definition equal to mu squared. If we're going to use this definition over here, well, this thing that we have over here is by definition equal to, well, Y overline squared. So therefore also this sample mean squared is going to converge in probability to mu squared. Well, another thing which is related is the so-called analogy principle. Well, in many situations, what we would like to estimate is some kind of estimate theta that we have over here. And theta is actually nothing else as the mean, the population mean of this gy that we have over here. Well, we do already know what population means are because of the fact that population means are nothing else as integrals. They are always integrals over the total support of this random variable y that we have over here. Well, and then what we're going to do is we're going to integrate, well, over either the density function or the probability function, depending, of course, on whether this is discrete or continuous. And we're going to do that with respect to this function gy that we have over here. Well, the analogy principle now says that it's always possible to estimate this, say, estimate that we have over here by instead using the so-called sample equivalent, the so-called sample mean of this population mean that we have over here. Well, what is the sample equivalent? Well, that's always equal to, well, no expectation, but we're going to have summation. We're going to sum over all the observations that we have, and we divide by n. That is what the, say, corresponding sample mean is of this population mean that we have over there. And then the analogy principle says that in this case, theta hat, the theta hat that we have over here, is going to converge in probability to theta. Well, again, we can look at an example. Suppose that we want to estimate, in this case, the second moment of y. So that is by definition equal to this thing that we have over here. Well, then we should realize that we can estimate that by the sample second moment, which is actually nothing else as the sum now over the yi squareds divided by n. And in this case, you should realize that because of the fact that g in this case is nothing else as, well, a function again, which is just a squared function, then actually the analogy principle immediately says that this is going to be correct. Well, we should take into account that many people say that the analogy principle actually is derived from the law of large numbers. However, many mathematicians may actually say, like, well, the analogy principle is not derived from the law of large numbers. It actually is the law of large numbers. And that is, in my opinion, correct. You should realize that at the moment that we are going to look here at a, say, function gy, where y is a random variable, then you should realize that, say, the random variable z, which is defined as gy, is of course also a random variable itself, and therefore what we could realize is that then, if at the moment that we're going to use the law of large numbers with respect to not y, but g evaluated in y, well, then we immediately get the analogy principle. I would like to go on with the next topic, and that's the topic of convergence and distribution. First of all, the definition. The random sequence Bn converges in distribution to a random variable b, indicates that the limit with respect to n going to infinity of the probability that Bn is smaller or equal to b is going to be equal to the probability that b is smaller or equal to b. Well, what you should take into account that at the moment that we're going to look at convergence and distribution, compared to, in my opinion at least, convergence and probability, that convergence and distribution is much simpler. And the reason behind that is because of the fact that convergence and distribution is actually nothing else as convergence in, I would say, the deterministic case. Because of the fact that the only thing that we now have to prove is that this, say, non-random sequence, this is non-random of course, because of the fact that even though this is a random variable, probabilities themselves are of course not random. So therefore this is a non-random sequence. The only thing that I have to prove is that it's going to converge towards this number that we have over there. So that is just standard calculus. The only thing which is not standard in this case is that we have to do this essentially for any value of b. So any potential value, so any value in the support of this bn, or maybe better to say in the support of this b that we have over here, well, for that we have to prove this thing over here. That is the only thing that it actually makes it non-standard. But apart from that, this is just standard calculus. Well, a very famous example of convergence distribution is the so-called central limit theorem. Again, suppose that we have a random sequence yi, where I again runs from 1 till n. We're going to assume this yi to be IID. And in addition to that, I'm going to assume that the mean of y1 is equal to mu, and mu is smaller than infinity. And we assume that the variance of y1 is equal to sigma squared, and also that is smaller than infinity. Take into account that this is actually, well, more restrictive than what we had with respect to law of large numbers, because of the fact that in the law of large numbers we did not make any assumption with respect to variance. Then the central limit theorem says that the stochastic variable, the square root of n, multiplied by y n overline minus mu, so the sample mean minus population mean, that is going to converge to a normal distribution with a mean equal to 0 and a variance equal to sigma squared. Take into account that we already know from the law of large numbers that this sample mean is going to converge to this population mean. So that means that, well, if we only would look at this part that we have over here, well, this part actually goes in probability to 0. However, since the square root of n is going to converge to infinity, we have no idea what the, say, multiplication of the square root of n multiplied by this part that we have over here is going to converge to. However, the central limit theorem says that under these conditions that we have over here, it's going to converge to a normal distribution. Okay, I would like to go on with something that we could call a little bit sloppy mathematics, but nevertheless I would like to look at this because of the fact that this is used quite often by econometricians. First thing I would like to do is not really something sloppy, and that is something that we already know, and that is that at the moment that we know that a particular random variable x is normally distributed with a mean equal to mu and sigma square is the variance, then at the moment that we have a constant c over here, then if we multiply that constant c with respect to the random variable x that we have, then we still have a random variable, and we even know that in that case it's normally distributed with a mean equal to c times mu and a variance equal to c squared times sigma squared. In addition to that, if we're going to add c plus x, then we still have a random variable, and also here we know that it's a normal distribution with a mean equal to c plus mu, and the variance is still equal to sigma squared. Well, now we're going to look at the sloppy mathematics. Well, that is that we are going to start with the central limit theorem. There's nothing wrong with that yet. So we do know that the square root of n multiplied by the sample mean minus the population mean converges in distribution to a normal distribution which is a mean equal to 0, and sigma squared is going to be the variance. Well, we should realize that this is of course correct, but it's only correct at the moment that n goes to infinity. So only in the moment that n goes to infinity, we're going to have here a normal distribution. However, now let's assume that at least approximately is the case that even in the case that n is not exactly equal to infinity but large, well then at that moment in time we have here equality in distributions. This is not completely correct, of course, because of the fact that even if n is very large, then we do not have here equality in distribution in terms of this normal distribution that we have over here. But suppose this is true. Well, then at that moment in time we can, well, first of all, divide the left and the right hand side here by the square root of n. If you're going to do that, then we're going to get this. Then the, say, sample mean minus the population mean now converges in distribution to 1 over the square root of n multiplied by this normal distribution that we have over here. Then the first thing we can do is that we can bring the 1 over the square root of n into the normal distribution. That looks like this that we have over here. So that means that we still have a normal distribution with a mean equal to 0, but the variance now is going to be equal to sigma squared of n. Then the next thing we can do is that we can bring this mu, or minus mu, we can bring it to the other side in order to get that the sample mean converges now in distribution to mu plus this normal distribution over here. And now we can use this relationship that we've over here in order to bring the mu into the normal distribution. That implies that we still have a normal distribution, now with a mean equal to mu, and sigma squared over n is going to be the variance, which implies that now the sample mean is going to converge in distribution to this normal distribution that we have over here. You might say that that cannot be correct because of the fact that the sample mean is not going to converge in distribution to something because of the fact that the sample mean, according to the law of large numbers, is actually going to converge in probability to this mean that we have over here, to the population mean. That is already what the law of large numbers says. There's nothing with respect to convergence in distribution. You still might say that this could be correct given the fact, of course, that sigma squared over n, if n goes to infinity, becomes equal to 0, which still says that this is now going to be a degenerate distribution, which is degenerate in this mu over here. However, if we're going to assume that this even holds at the moment that n is not really infinity, well, then what we're going to get is that we're going to get a normal distribution with a variance that can be seen as, say, this variance that we have over here, for a finite n that we have over here, and that is actually what is typically reported at the moment that we're going to look at, say, results of econometrics. And this, because of the fact that this is used so many times in econometrics, has a very special name. It's called the asymptotic variance. I'm going to use this notation for it, and it's simply always equal to, say, the sigma squared that we had divided by the n that we have over here. And you should realize that especially at the moment that we're going to look at results from regression, then the standard errors of regression coefficients is actually based on the square root of this thing that we have over here. Well, like we had the continuous mapping theorem in the case that we had convergence and probability, we also have Slutsky's theorem. And Slutsky's theorem states that, well, if Bn is going to converge in distribution to B, then we also have, for a continuous function g, that gbn is going to converge in distribution to this gb that we have over here. Also, in the case that we have Bn to converge in distribution to B, and Cn converging in probability to C, so take into account that here we have two types of different kinds of convergence, here in distribution and there in probability, then Bn multiplied by Cn converges in distribution to B times C, and Bn plus Cn converges also in distribution to B plus C. So what you can see is that even though we have here convergence in probability, in the end, if you multiply or if you add these things up, it's always going to be convergence in distribution. I would like to go on with a next topic, and that's the topic of M-estimators. What we should realize is that in many situations in econometrics, we could actually, or we are looking for an estimator that I here denote by theta hat n, that's actually nothing else as a solution to this, say, root problem that we have over here. So we sum over a particular function psi that we have over here, which is a function of yi, and this theta hat n that we have over there. We sum in such a way that this becomes equal to 0. But of course, if this is equal to 0, we can also actually put there in front 1 over the square root of n. Well, as I already said, many estimators in econometrics actually look like this estimator that we have over here. For example, at the moment that we're going to look at the maximum likelihood estimator, the maximum likelihood estimator is a special case of this, because what we do in the maximum likelihood estimator is that we minimize the likelihood function. And that's of course nothing else as setting the, say, first order derivatives of the likelihood function equal to 0. This looks a lot like that what we have over there, with of course psi replaced by this, say, first order derivative that we have over here. But also in the case that we're going to look at nonlinear least squares, we're going to see that nonlinear least squares is a special case of this estimator that we have over here, which is, by the way, usually called an M-estimator. Here we have yi is equal to gxi theta plus ui, and what we would like to estimate over here is this parameter theta. Well, we already know that we typically in nonlinear squares are going to do that as follows. We are going to minimize the sum of squared residuals, this thing that we have over here. We're going to, well, pick this theta in such a way, we call that of course theta hat n, in such a way as this is going to be minimized. Well, that means of course nothing else is that we're going to look at the first order condition. This is the first order condition of this minimization problem that we have over here, and also here we immediately see that this is actually a special case of the, say, well, general problem that we have over here. But also method of moments are a special case. What we should realize is that if this is the method of moment estimator, where we here have, say, the mu hat, and here we actually have nothing else as a higher order moment. Well, then what we can do is that we can bring this to the other side, and we get of course a 0 here, now at the right hand side, and I can bring this mu hat into this sum that we have over here, and then also here we are going to see that we almost already have exactly the same thing as what we had the previous slide. What I still can do is to multiply the left and the right hand side by square root of n, and then I get exactly. So also method of moments estimators are actually special cases of the thing that we had at the previous slide. Concluding from this, we can say that the estimator that we have over here is often used in econometrics. As I already said, therefore it has a special name and it's usually called an M-estimator. Now it might be so nice if we can say very general things about these M-estimators, such as, well, what we can say is that we could ask ourselves the question, when, under which conditions is this estimator that we have over here, when is it going to be consistent? Well, for that we can say first of all that at the moment that we're going to look here at the left hand side, then this looks like a simple mean. It's almost already a simple mean. The only thing that we need to do is that we have to multiply this by 1 over the square root of n, and that's of course no problem because of the fact that we can do that, because then this is still going to be equal to 0. So therefore we can say that what we have here at the left hand side is a sample mean, and we do know that sample means, according to the analogy principle, they're going to converge to the corresponding population means. So therefore the population analog of this relationship that we have over here is this relationship that we have over here. Now the most important condition is going to arise, because suppose now that we are going to be in a situation in which we can prove that the unique solution of this relationship that we have over here is that Q is going to be equal to theta, where theta is, say, the real value of the estimate that we try to estimate. So the value, the object that we try to estimate. Theta is the real value of that particular object. Well, then in a sense you can prove that theta hat n is going to converge in probability to this theta. And the reason behind that is because of the fact that you should realize that this thing that we have here at the left hand side, being in fact the sample mean, is going to converge to that thing that we have there at the left hand side. Not just for one particular value, but it's actually going to converge for any value of this q that we have over here. So that means in fact nothing else that if n goes to infinity, then this thing that we have over here at the left hand side is going to converge to, in a sense, the same function as that thing that we have there at the left hand side. But if they are the same function, if n goes to infinity, of course they also will have the same, I would say, unique solutions. They will have the same unique roots. And because of the fact that we do know that the unique solution of this thing that we have here at the left hand side is this real value theta, that means of course that this thing that we have here at the left hand side, well, the solution of it should also converge to the theta we have over there. So that means nothing else that under this condition that we have over here, that q equal to theta should be the unique solution of this, say, problem that we have over here. Well, that is the main criterion that we actually need for consistency of this theta hat that we have over there. I would like to go on with the next topic, and that's the topic of the asymptotic distribution of the M-estimator. For that, what I'm going to do, first of all, we should realize that this is, of course, our M-estimator. And what we now are going to do is that we're going to use a Taylor series expansion. I'm going to use a Taylor series expansion around the true value of theta. And I just denoted that by just theta as we have it over here. So that means that the first term in the Taylor series expansion that we're going to get is simply this term that we have over here, which is exactly equal to that term that we have over there, but then with, instead of theta hat, we are going to have theta. And then the second term that we're going to have, well, that's of course always the first order derivative of this term that we have over here with respect to theta. So then we get this thing over here, and we now are not going to evaluate it, of course, in theta hat, but we instead are going to evaluate this thing again in theta. Then we always multiply this by the difference where we're going to evaluate our function, that is in our case theta hat, minus where we approximate it, and that's in theta. So therefore we get here theta hat n minus theta. And then the final term that we're going to have is usually called the rest term, or maybe better to say the order term. From calculus, you know that that is usually in this case O1. But in this particular situation, it's going to be a little bit different. And the reason behind that is because of the fact that we should realize that what we have here are stochastic terms. This term that we have over here, that term, and even this term that we have over here is stochastic. And the reason behind that is because of the fact that this y that we have over here is stochastic. It is data, so therefore it is by definition stochastic. And that is the reason why we're not going to use the standard order terms, but we're going to use stochastic order terms. That's the reason why we have this subscript p that we have over here in order to indicate that this is a stochastic order term. OP1 here means actually nothing else than that we're going to look here at the random sequence that is going to converge to 0 at the moment that n goes to infinity. And we always multiply this by the highest order that we have with respect to our Taylor series expansion, and that's of course is theta hat n minus theta. Now we should realize that this term that is over here is also going to converge towards 0 at the moment that n goes to infinity. And the reason behind that is because of the fact that we already know that theta hat n is a consistent estimator of theta, so therefore theta hat n is going to converge towards theta at the moment that n goes to infinity, so therefore this difference is going to converge towards 0. And now we should realize that because of the fact that we have this order term that we have over here, by definition it's the case that these three terms that we have together must be equal to this term that we have over here. And that term is equal to 0. So therefore also these three terms that we have over here are equal to 0. And then the first step that we can take is that I'm going to multiply this term that we have over here by the square root of n divided by the square root of n. That's very nice because of the fact that then these two square root of n's that we have over here, well, they will just become n. And this square root of n, I can take it here in order to get here a square root of n multiplied by theta hat n minus theta. And the reason behind the fact that this is really nice is because of the fact that what I actually want to do is that I would like to get the asymptotic distribution of this estimator theta hat that we have over here that means actually nothing else is that I would like to get the asymptotic distribution of the term square root of n multiplied by theta hat n minus theta. You have no idea yet what is going to be, but what we can do now is that we could now try to write it in such a way that I have here at the left-hand side, I have this thing over here and everything else on the right-hand side. Well, that I'm going to do over here. Here I just have written down that thing that we have already there. But now what we're going to do is that we first of all are going to bring this to the other side in order to get this relationship that we have over here. I can actually also bring this to the left-hand side, but that I will just again have OP1 multiplied by this thing over here. And I can divide, of course, the left and the right-hand side by this term that we have over here. Then we get exactly what I wanted. The left-hand side now we have the square root of n multiplied by theta hat n minus theta. We have here now a lot of things at the right-hand side. If I can prove that this thing we have here, the right-hand side, is going to converge in distribution to something, so of course it's going to be the left-hand side. So that's the next thing that we're going to do. We're going to simply try to find out what this is going to converge to. And the first thing we can do is we can actually look here at the numerator. I'm not going to say too much about this term over here because that is going to converge towards 0 very quickly. So let's first look at this term that we have over here. First of all, I can again multiply this by the square root of n divided by the square root of n, as I do over here. Then these two square root of n's, they will just give me an n. And I get the square root of n here. Now we should realize, as we have seen earlier in this video, that a sample mean, this is actually nothing else than sample mean, multiplied by the square root of n, is always going to converge in distribution according to the central limit theorem. Is at least under certain restrictions, it's going to converge towards a normal distribution with a mean equal to the corresponding population mean and a variance equal to the corresponding population variance. Where what is the population mean of this thing that we have over here? Well, that's again very simple, no summation, but expectation. We're going to take the expected value of this first element that we have over here. We're not going to divide by n anymore. That means that what we're going to get is this mean that we have over here. So according to the central limit theorem, the mean that we're going to get is this thing that we have over here. What is that? Well, that is of course equal to this thing that we have over here. And we actually already know that there's actually only one solution of this thing over here. This thing actually has a unique solution for the case that theta is exactly equal to the correct theta, because we know that then it actually equals 0. So then we should realize that we know already from the, say, condition that we have seen before with respect to consistency, this thing that we have here, the left-hand side must be equal to 0. Well, the asymptotic variance, as already said, is going to be the population variance, and that's actually nothing else as, well, in this case, it's just a second moment because of the fact that the first moment squared that we typically have with respect to the variance is always equal to second moment minus the first moment squared. But the first moment is in this case equal to 0. So therefore it's just a second moment of, well, the corresponding second moment of this thing over here, which means actually nothing else. We simply have to square this thing over here. So therefore we're going to get this for our asymptotic variance. Take into account that that's actually only the asymptotic variance here of this numerator that is over here. I haven't said anything yet about the denominator, but the denominator is somewhat simpler. It's actually nothing else as a, well, it's a sample mean. We do know that sample means actually going to converge in probability towards their corresponding population means. So that means no longer summation, but expectation. Going to take this expectation over the first term that we have over here, we no longer divide by n. In order to realize that, I have here another time the denominator is going to converge to this term that we have over here. And that implies that an M-estimator, we had, of course, a numerator divided by the denominator. We know that the numerator is going to converge, well, again, to 0, of course, if we're going to look at this. Numerator divided by the denominator, of course, is also, the mean is going to converge towards 0. And the variance is simply going to be equal to the variance that we had with respect to numerator divided by the denominator as we have it over here, but squared because of the fact we have here a variance. So that implies, by definition, that an M-estimator always is going to converge towards a normal distribution with a mean equal to 0, and the variance simply is going to be equal to this term that we have over here.